This is lesson 1 in the Advanced Higher Physics Uncertainties unit. In this lesson, we're going to introduce you to the idea of measurement, the meaning of uncertainty, the difference between accuracy and precision, and remind you of what is meant by a best estimate. So let's begin by considering what we mean by counting. If you look at the triangles appearing on your screen, we can count these triangles quite easily because there is a fixed number of them and they're not changing. They're not appearing and disappearing, for example. So when we count them, we produce an exact number. Count these triangles now. I'm sure you all discovered there were 8. Note then that this is an exact value. There is no uncertainty in that number 8. There's no possibility that there are 7 triangles or 9 triangles. There are exactly 8. No uncertainty in counting. In physics, of course, we spend far more time measuring physical quantities rather than counting objects. And when we measure a physical quantity, we never produce an exact value. It's impossible. There will always be uncertainty in our measurement. Here's an example. What voltage is measured here? I'm sure you all spotted. The reading is 16.8 volts. What's the error in that measurement? Now draw upon your knowledge of higher physics to answer this question. Well, it's a digital scale, and so the error in the measurement is quoted as plus or minus 0.1 volts. The last decimal place tells us what the error is. Here's a question though. What does that mean? What does it mean to say the error in a measurement is plus or minus 0.1 volts? Well, what that means is that provided the meter is properly calibrated, that means compared in the factory with a standard voltmeter whose measurements are known to be accurate, then we can know with confidence that the voltage lies somewhere between 16.7 volts and 16.9 volts, with the best estimate being 16.8 volts. So we don't know exactly what it is. Could be 16.81, 16.82, could be 16.79. We just don't know. What we do know is that the best estimate is 16.8 and that the true value of the voltage lies somewhere in between 16.7 and 16.9. And that spread of possible values is a measure of the uncertainty in our measurement. So we say the voltage read is 16.8 plus or minus 0.1 volts. V, of course, is the quantity we're measuring, in this case voltage. 16.8 is the best estimate, and the plus or minus 0.1 volts is the error in our reading. An error refers to the uncertainty in an individual reading, and in this case, it's an absolute error. We're now going to look at some technical terms, rather important technical terms, the first of which is accuracy. Let's do a little thought experiment. Let's imagine we want to measure the width of a wooden beam with a ruler. And we know that the true value of the wooden beam is 8 centimeters. That's shown in the diagram. So we take our ruler and we measure the width of the beam. And measurement 1 gives us 8.5 centimeters width. So slightly out from the true value, but with one reading, that's our best estimate. So we measure it again. And this time we get a measurement number 2 of 9 centimeters. So clearly we're not very good at measuring, but this is simply a thought experiment. Well, hopefully you'll agree that measurement 1 is closer to the true value than measurement 2. You can see this looking at the arrows in the diagram. They show you how measurement 1 is closer to the true value than measurement 2, and therefore measurement 1 is said to be more accurate than measurement 2. So the closer you are to the true value in your measurement, the more accurate your measurement is. And that leads us to a very simple definition of accuracy. An accurate measurement is one that is close to the true value. An accurate value is said to have a small error, and that's if we have a single reading. So when we have a single reading, we've only measured something once, and we're aware of the difference between our measurement and the true value, we call it an error. An accurate value is said to have a small uncertainty if it results from the average of repeated readings. So uncertainty is the technical term used when we have repeated readings which have been averaged and we're quoting the uncertainty. If we've only done a single reading, then the uncertainty is known as an error. You'll often find people using these two terms, error and uncertainty, interchangeably. Technically, you should only call it an error if you're referring to a single reading. It's not going to be a major issue though. Okay, let's try an example. Imagine you're measuring a voltage from an AC power supply, and you know from the factory calibration that the voltage is 235 volts. That's the true value. Which of the following measurements is more accurate and why? Well, I hope you can see that meter A is reading 230 volts, but meter B is reading 241. 230 is closer to the true value of 235, and so is more accurate. So much for accuracy. A term which is often confused with accuracy is precision. And just as accuracy is a very clearly set out definition, so does precision. So imagine we have a measuring cylinder with some water in it, and we want to measure the volume of the water. Well, you can see that in the diagram we've zoomed in on the meniscus. The meniscus is the curved shape which water takes in a measuring cylinder like that. And for accuracy, we always measure to the bottom of the meniscus. Well, let's think of a few questions. What is the volume of this water to one significant figure? Pause and answer that now. Well, to one significant figure, you would quote the volume as being 0.02 litres. You can't really go to millilitres, because if you use the milliliter scale, you will be forced to go to two significant figures. The second zero would be significant. So 0.02 litres is the answer to one significant figure. What would the volume be to two significant figures? Well, that would be 21 millilitres. You can see that in the central diagram. Or you could call that 0.021 litres. But I'm going to call it 21 millilitres. Now, it is clear from the magnified diagram that the reading is somewhere between 21 and 22. But if we're forced to go to one significant figure, we need to basically make a judgment call and say, well, is it closer to 21 or is it closer to 22? I'm going to say that I think it's closer to 21. And finally, estimate, and I emphasize estimate, the volume of this water to three significant figures. Pause and try that now. Well, probably the best you can do there is to note that the meniscus lies somewhere between 21 millilitres and 22. It looks like it's almost halfway between the two. So it looks like the best estimate there would be to say it's 21.5 milliliters. You could call that 0.0215 litres if you wish. So 21.5 is 3 significant figures. Which measurement do you think is most precise? Well, it may not surprise you to learn that the most precise of those measurements was the one given to 3 significant figures. And that brings us to the definition of precision. A precise measurement is one that can be confidently quoted to a large number of significant figures. So the more significant figures, the more precise the measurement. Now, many factors can affect precision. Often it's the quality of the measuring device which determines precision. So, for example, the measuring cylinder above allows us to estimate to the nearest 0.5 milliliters reasonably well, because your eye can see that meniscus is roughly halfway between the 21 line and the 22 line. But I don't think you could confidently measure that volume to 1/10 of a milliliter. Possibly a half milliliter, but not 1/10. You would be guessing quite a bit. So a different measuring cylinder, one that had been very carefully made with 0.1 milliliter graduations in it, that might allow us to go to 1/10 of a milliliter, but not the one we have. So the quality of your apparatus often determines the precision that you can achieve. So how do accuracy and precision relate to each other? Well, if you look at the diagram, the x-axis is the width of the beam. It's recording the measurements, if you like. So imagine that we do quite a number of measurements of the width of this beam, either one person doing lots of measurements or possibly a whole class of 20 people doing one measurement each. You would typically find there would be a range of answers. Now, the true value is 8 centimeters. Let's imagine, though, that when we got, say, 20 people to do their measurements, that there was a spread of measurements and that the measurements were clustering around a value that was bigger than 8 as shown. So the best estimate would be the average of all those measurements. It would occur at the central part of that peak. And the spread of the measurements, the spread of that curve, is a measure of the precision. So a really precise set of measurements would have quite a narrow peak, and a less precise set of measurements would have a wide peak. Notice, though, that our best estimate in this thought experiment is really quite far away from the true value. So the distance that best estimate is away is a measure of the accuracy. The more accurate the best estimate, the closer the best estimate line will be to the true value line. And precision comments on how wide the spread of readings actually is. So, if measurements are known to a high degree of precision, remember that means a high number of significant figures in our measurement, then when we repeat the readings, the measured values will cluster close together. The peak in that curve will be quite narrow, will not be very well spread out. The height of the curve, in this case incidentally, shows the number of readings at a particular measurement, and they're clustering around the best estimate. The spread of the curve shows how close the readings are to each other, and that's an indication of precision. So the closer the cluster to the true value, the greater the accuracy. And on the right then the graph is showing a fairly sort of precise set of measurements because the curve is quite narrow, it's not too well spread out. However, the best estimate is not very good, it's not a very accurate measurement, because it's quite far from the true value. So it's possible to have a best estimate which results from quite precise readings, but which is nonetheless not that accurate. And just to finish off then, you can see a number of scenarios here showing you different types of accuracy and precision. So if we look at the top left graphic, there you can see the true value is the dotted line on the left, the vertical dotted line on the left, and the best estimate is the vertical dotted line on the right. Well, that's quite low accuracy because the best estimate is quite far away from the true value. And that particular curve is quite sort of wide, so it's not that precise either. So some of our readings were way above the true value, and some of them were much, much closer. But the difference between the biggest reading and the smallest reading is really quite big. So low accuracy and low precision in the top left graphic. The top right graphic, well, look at the best estimate. It's still quite far away from the true value, so that's still fairly low accuracy. However, it's got higher precision because although our measurements are not particularly accurate, they're all quite clustered close together. So that suggests we're measuring them with a good deal of precision, but nonetheless, our measuring device isn't returning a very accurate measurement. The lower left graphic, well, if you look at the best estimate there, it's actually quite close to the true value. So that's a fairly accurate measurement on the whole. Our best estimate anyway is quite accurate. However, to get that best estimate, when we took our average, we're taking an average of readings that are quite widely spread. So we've got quite low precision there, but reasonably high accuracy. That's a situation where your measuring instruments maybe not greatly precise, but if you do enough measurements, the ones that are much too big and the ones that are much too small are sort of balancing each other, and you end up homing in on a reasonably good best estimate. And then finally, the last diagram on the lower right, well, our best estimate is lying right on top of our true value, so that's very accurate. So that's high accuracy. And it's quite a narrow spread. The curve's quite thin, so that's quite precise as well. So there we are, the difference between accuracy and precision. Make sure when you're using these technical terms, you use them in a very correct way.